Hello YouTube, I'm back for another video, and today I'm going to talk about series. So we're doing a Mathematica tutorial on series. Okay, well let's get started. The first question here says, show that the series, the sum from 1 to infinite of e to the power of n over n factorial converges. Okay, now I've got the ratio test here. So we'll do this with the ratio test. And it says that, well, look, it's a test on whether or not the series, the sum of the an as n goes from 1 to infinite, the test on whether or not this converges or diverges. So what we do is we take the limit of the n plus 1th term divided by the nth term, but its absolute value. We take the limit of this as n goes to infinite. That is, we consider this when n takes on very large values, in fact infinite values. All right, now this will denote by an uppercase L. And so this test says if L is less than 1, then the series converges absolutely. And that means that the sum of the absolute values of the an converges, and hence the series itself, the sum of the an has to converge. Okay, and if L is greater than 1, then the series diverges, but if L is equal to 1, then the test is inconclusive. Right, so this is the ratio test. Now let's have a look at it for this particular problem. Okay, but first, before we do that, let's just calculate using Mathematica the first few terms of this series. Okay, now we can enter this using sum. So sum, and let's say we'll take this from 1 to 10. All right, now let's enter. Let's see, we want exp 1 to the power of n, so e to the n, and then divide this by factorial n. Okay, let's have a look. All right, and we have e plus e squared on 2 plus e cubed on 6 plus e to the 4th on 24, and so on. We've only got 10 terms of this sequence. Now we might want to have the numerical value of this sum, you see. So let's now just put an uppercase N around this and see what we have. Okay, 14.15. But now what if we want to view this as we take our sum higher and higher? Okay, so rather than use 10 at the end of the sum, let's put an M there. All right, now that we have that, we can say tabulate over the m. So let's do this, table, and we'll table the m from 1 to 10. Okay, shift enter, and we can see these increasing. Right, so why stop at 10? Let's go to 100. Okay, so we go to 100. And well, look at this. It looks as though these are converging to 14.1543. All right, so that's a good sign that it's possibly true that this series is converging. So let's have a closer look by taking this numerical approximation in more decimal places. Okay, so let's take this to 50 decimal places and have a closer look at this. Right, so each of these are now taken to 50 decimal places, and let's investigate the the 99th and the 100th terms of this and see how they are different. They look much the same, so this seems to be converging very quickly. All right, in fact, these are the same to 50 decimal places. But they seem to be different somewhere in the middle here. Okay, all right, so this suggests that this series might converge. Now let's semicolon that, suppressing the output, and let's get on with our demonstration using the ratio test that this series converges. Okay, so AN, I will copy this because I already have the notation pulled out from the palette. So AN, and I'm just writing out, I'm not intending to calculate this, just writing out the demonstration that this series converges using the ratio test. Okay, so we have, now I want a pretty fraction, so I'll open up the palette again and I'll show you what I'm doing. Clicking this button, so I get a nice pretty looking fraction, and we'll put in e to the n, and in the denominator we have n factorial. Right now I wouldn't want to press shift enter here because this is a variable, right? It's not that double struck e, which represents the base of the natural logarithm. Okay, so I'm just using this more or less in comment form, right? But I'll put the comment symbols on later to turn that into a comment, but it just looks a bit better now. Okay, so we have AN is this, right? Now let's write down what AN plus 1 would be, right? So AN plus 1, well, we would change the exponent to an n plus 1, and then we would change this denominator to be n plus 1 factorial. Okay, now we want to look at the ratio AN plus 1 over AN. All right, so this, exactly this. And now I'll put vertical bars around to suggest that I'm referring to the absolute value. Now, this is not what you would do in Mathematica. You would write ABS with a square bracket, right? But I am just using this basically to type. Okay, so that's why this is purple. Now, this is equal to the absolute value of a fraction. All right, AN plus 1 is this, which I'll paste here. AN is this, which I'll paste here. Okay, and now let's simplify this. All right, so I could, do this manually, but let's just go down here and we'll type this in as it would be in Mathematica. All right, so I'll write ABS, and then we have a fraction. Right, the first thing is EXP, or e to the power of n plus 1, and then this is factorial n plus 1. Okay, so that's AN plus 1, and then we are dividing this by AN. Well, I've got factor, but I want factorial. Factorial. Okay, so let's try shift enter, see what we have. Okay, so this is saying that it's e to the power of 1 multiplied by the absolute value of n factorial over n plus 1 factorial. Right, but we know what that is. So I wonder if we can write simplify. Let's try this, simplify see if we get a simplified expression. No, not in this case. So that was not helpful. Okay, so now we can say that this n factorial is n times n minus 1 times n minus 2 dot 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 all the way down to 1. And likewise, this denominator, so I'll just write this out. The denominator is, well, we don't need the brackets. Okay, so I can write the denominator like this. And now we can cancel the n factorial. Okay, so let's write again, and we will cancel the n factorial. Notice now that the n, since it's positive and we are taking the limit as n goes to infinite, well, we don't need the absolute value anymore. So we can just get rid of this, put this up here. All right, and so this is e over n plus 1. Okay, so that is the absolute value. Now I'll copy this and go back up here to this, and I'll paste that there. Okay, and so next we want to consider the limit as n goes to infinite of this. All right, so let's just continuing in our comment form limit. Now I've already got that written up here. Okay, limit as n goes to infinite of this is equal to the limit as n goes to infinite of this fraction right here, e over n plus 1. All right, well, you don't have to think very hard to see what happens when n gets large in this fraction, right? Because e is constant, 2.71828, etc. But the n are getting larger, okay, as n goes to infinite. So we have this limit being equal to 0. All right, and now 0 is less than 1, so we can conclude, right? So therefore L is less than 1, so the series converges absolutely. Okay, and now let's just actually put this in comment form since we have already talked about it. And we don't need it to be so bright and beautiful. Okay, so that means that this series converges. All right, so that's that one done. Now, we may as well talk about some of the other cases, right? So if we were considering the series, the sum from n equals 1 to infinite of n factorial over e to the n, well, that one would diverge because you would find out that you would have L greater than 1, and so the series diverges. Now, how about an example of this case? Well, there are many. Okay, but one that comes to mind is the sum. Let me have a look at my notes. All right, so we'll go down here and we'll enter a sum n goes from 1 to say 10. All right, so this, we'll start with a finite sum. And let's talk about the fractions. I'll copy a fraction in. And I want to talk about -1 to the power of n plus, let's see, we're starting with 1. Okay, so n plus 1 can go there. And then in the denominator, I want 2n plus 1. All right, so these are alternating in sign, the terms of this series. are alternating in sign, and the denominators are the odd numbers from 1 on up. Okay, so really, now I should probably put this in comment form. Okay, so what I'm talking about the sum 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9 minus 1 over 11, and so on. All right, this is the sum I'm talking about. Okay, so let's just look at the sum of the first 10 terms of the series. All right, well, we have a fraction. Okay, now let's take a numerical value of that, just as we did before. N, okay, so 0.191921. Okay, now let's change this 10 to an M and tabulate over these. Table. And we'll tabulate M going from 1 to 100. Why not? Okay, so we start with a third, then 0.13, etc. And let's have a look. These look like they might converge as you scroll down to 0.2121. No, actually, they're not converging. They're not converging rapidly. Okay, so it looks to be like it might be converging, but perhaps not quickly, right? Because this is only 100 terms out of infinite. So let's increase this to 1,000 and have another look. Now it takes a little bit longer to run. Okay, let's scroll down. Scroll down, so it looks like 0.21. All right, 0.214. Now the 1,000th term seems to be 0.214352. All right, however, this fourth decimal place is still different. So these seem to be converging, but not quickly. Okay, now that we've seen that, I'm going to tell you what this series actually is. This is a famous series. All right, let's now multiply it by 4 and have another look. Okay, so I'll just put a 4 space and try this again. Okay, we'll scroll down. Scroll down. Looks like 0.85. Well, no, this is not what I was expecting at all. So, knowing what it is myself, I will have to go quite a lot farther to show you what this series actually is. Okay, so let's go to 10,000. All right, and rather than tabulate it, let's just get rid of the tabling to speed this up a bit. And we'll go change the M to 10,000. Just shift enter. 0.85. 0.85. Did I get this wrong? Possibly. 20,000. Okay, 100,000. Waiting. Okay, it's still at 0.85, 8397. All right, so this is probably converging extremely slowly from what we can see. All right, because this series actually converges to pi. All right, it's well known. for converging to pi. Now, if I open up, not that, if I open up Wikipedia, which I've already closed, you can see that it converges to pi. Okay, but let's consider this in the context of the ratio test. All right, so let's consider the sum of these. All right, so an is equal to this, and I'll go up here and I'll find an an. Okay, an is this. Now what about an plus 1? An plus 1, well, we add 1 to the n, so we end up with a plus 2. And then if we add 1 to this n, well, this is simply equal to 2n plus 3 in the denominator. Right, so 2n plus 3, and then the numerator is, well, minus 1 to the n times minus 1 squared, but minus 1 squared is just 1, so I can get rid of this. Okay, now we are interested in the ratio, so let's copy a fraction. An plus 1 over an is, so we have this in the numerator, and then we have this in the denominator. Okay, so let's simplify that. Now, let's see, we can multiply top and bottom by 2n plus 1. All right, so we'll copy this, paste it here. Top and bottom by 2n plus 1. So we put it there, and we put it there. Okay, what that does is it cancels this with this. All right, and now in the denominator we have minus 1 to the n times minus 1. Okay, so let's write it in that way. So minus 1, and then the minus 1 to the n there and the minus 1 to the n there can cancel, so let's get rid of those. That becomes a 1, and I can take this and put it in the numerator there. Okay, and put that minus 1 out the front. All right, so this is the ratio of an plus 1 over an. Now, the absolute value of this ratio, all right, so I'll just write ABS for absolute value. Absolute value of this is just the positive one. All right, so just that there. Now, we are interested in the limit. Okay, so limit as n goes to infinite. Now, where is that? Here. Okay, scroll down, limit as n goes to infinite of this is equal to limit as n goes to infinite of this little fraction here. Okay, now to evaluate that limit, what we want to do is divide numerator and denominator by n. Okay, so let's do that. When we do, we have 2 plus 1 on n and 2 plus 3 on n. Okay, and now we take the limit, and this goes to 0, and this goes to 0. All right, so we have the limit as n goes to infinite of 2 over 2, which is equal to 1. Okay, now what does that say in terms of the ratio test? Well, it says it's inconclusive, right? We know that this series should converge to pi on 4, but the ratio test here says that by the ratio test, you cannot deduce that the series converges. Okay, so let's write by ratio test inconclusive as to whether or not it converges or diverges. Okay, so you'll have to show that it converges to pi on 4 by some other method. All right, so in summary, the ratio test is great, but there are some inconclusive cases. All right, so that's all for now. Hope you enjoyed this and learned something. Please don't forget to like, subscribe, and comment. Okay, I'll see you next time.